Okay, so in this question we have two identical containers. They're open at the top, connected at the bottom via a tube of negligible volume and a valve that is closed. The container to the right is filled with mercury at a height of 1 meter, and the container at the left is filled with water, also at a height of 1 meter. The valve is open, and then the water and mercury would move, and we want to find the fluid level in the left container when equilibrium is re-established. Now we know that since mercury is more dense, then it's going to flow towards the left container and it will push the water upwards. And we can now study some pressures at different points in order to try to find the new height that we will have after the valve is open. So if we want to see the new scenario that we have here, now as we said, the tube connecting the two liquids has a negligible volume. So this is the mercury. It will flow towards the left container and push the water up. So I guess this figure can show us and give us an idea of the new heights of the liquids and how this whole thing would look like after equilibrium. Now, what we want is to find this new height. It was 1 meter, and now we don't know the new height. To find this height, we can consider some points, like I said. So maybe we can consider the point at the bottom, because above this point we will have this height h, and then maybe we can solve to find this h. And we can say that this point at the bottom in the left container will have the same pressure as this point at the bottom of the right container. So if I label these 2 points to be A and B, the pressure at A equals the pressure at B, since both are at the same horizontal level. And then we can say that the pressure at A is equal to rho GH for the first liquid, because we can see that here we have mercury and then here we have water. So we have different heights to consider. Let's name this H mercury left. This is H of water. And the height here above B, I will name it H mercury right. So at A, what do we have above A? We have first the liquid of mercury with a height of H mercury left. And above this mercury, we have a height of water of a height HW or H water. And above that, of course, we have the atmospheric pressure. And we can consider that as well in stating the values of the pressures at the two different points. So again, this is mercury left, height of mercury left. Sorry, the density here, I can just write it as density of mercury. So then we add the pressure exerted by water at this point. The water has a height of HW plus the atmospheric pressure, like we said, and this is equal to the pressure at P, which is rho of mercury, height of mercury right, times G plus the atmospheric pressure again. Now, of course, this atmospheric pressure would cancel out. The G's would cancel out here, and we can end up with this equation. Now, if we look at this equation, what do we know? We are given the height of, we are not given any of the heights actually. We are given the densities of water, the density of mercury. We have the heights before opening the valve. So these are now different, but we can make use of the previous heights with one thing. We know that the height of mercury in total is equal to the height of mercury in the left plus the height of mercury in the right. Since both containers have the same area, so the height that we will have should be in total the same before and after opening the valve. And this is equal to 1 meter, right? The height of mercury is equal to 1 meter. The height of water is equal to 1 meter as well. And we still have the same height of water after opening the valve. So the height here must be 1 meter. So now we can just solve these two equations. So maybe if I solve here for the height of mercury in the right and substitute this in the previous equation, I would get 1 minus the height of mercury in the left. So I will substitute, and let's name this equation star. And this would give us rho of mercury, height of mercury on the left, plus rho of water, height of water equals rho of mercury into 1 minus height of mercury on the left. Now we can rearrange this to find the height of mercury on the left, and this would give us, let's see, we have rho of water, height of water with a minus sign, plus rho of mercury, and we have here 2 rho of mercury, so we will divide on both sides. So we get 1 over 2 rho of mercury into rho of mercury minus rho of water, height of water. And we can simplify this into half times 1 minus rho of water over rho of mercury. And this gives us, if we substitute the values, this is 0.5 into 1 minus, the density is 1000 for water. The values are not given here, but we know them from literature. The density of mercury, I think it's 13,600. Let me just check. Yes. And the final answer here would be 0.46 meters. So this is here the height of mercury on the left. Now we want the fluid level on the left. We want this whole value H. And H is obviously the height of mercury plus the height of water. Height of mercury on the left plus height of water. Just found this to be 0.46, and the height of water is 1, so this is 1.46 meters. This is the height of the fluid on the left section after opening this valve here.